This video today is going to be on ions and oxidation numbers, as well as polyatomic ions. So first off, what's an ion? Let's start with what an atom is. And an atom is something that is has equal numbers of protons and electrons. So if I'm talking about, just like carbon, carbon will have 12, all carbons have 6 protons. They have to, because that makes them carbon. And if it's an atom, that means it also has 6 electrons. Same situation with, say, hydrogen has 1 proton. And if it's an atom, it has 1 electron. So since the protons and the electrons are charged, when you have equal numbers of protons and electrons, then there is no charge overall. So this is a +1 and this is a -1, or sorry, a -1, and so that equals 0. Over here, there's a +6 and a -6, that equals 0. So the overall atom has a charge of 0. So when you grab a piece of charcoal, it doesn't shock you, because there are the exact number of pluses and minuses, even though there are billions and trillions of them, that's still exactly the same number. So what's an ion? It's when those numbers are not the same. So if I'm looking at an atom of hydrogen, except it shows a +1 charge on it, how do I get something with a +1 charge? There's only one option. Hydrogen has 1 proton, and it can have, its atom form has 1 electron. I cannot make this 2 protons. If I turn this into 2 protons, this ceases to become hydrogen and becomes helium. Plus we can't do that. Or, well, we can't do that. Maybe it's possible, but we don't know how to do it. Not like this. So the only way to get something that has no charge to have a positive charge is if it loses the electron. And so now it's got a +1 charge, but there's no minus charge. So this has an overall plus charge. So if an atom becomes positively charged, then that atom has lost an electron. So what happens if it becomes negatively charged? Let's go right back to that. I've got a hydrogen atom, and it has 1 proton. And its atom form has 1 electron. But in its ion form, its anion form, its negative form, it can have 2 electrons. And so now I've got a +1, and I have -2, leaving me with a -1 charge. So this is no longer a hydrogen atom, it's a hydrogen ion. So what an ion is anytime protons and electrons within an atom are not equal, then I've got something called an ion. And the best example of that would be table salt. When I taste something salty, I'm actually tasting sodium, but I'm not tasting sodium with a 0 charge. I'm tasting sodium with a +1 charge, because sodium has lost 1 of its 11 electrons. And so this is something my tongue can taste. We had a discussion about this during Why I Like Chemistry. That will blow up your face. Actual sodium atom, because it's trying to get rid of 1 electron to turn into this, because that's what it wants to be. All right, so the names for anions and cations are, the positive ones are called cations. So I have this stupid graphic here to hopefully trigger your memory into remembering that positively charged ions are called cations, and negatively charged ions are called anions. Ions and cations. So both ion on both of them, but cat is the positive one and an is the negative one. Okay, so how does an atom become a positive ion? It loses an electron. How does an atom become a negative ion? It gains an electron. Could be more than 1 electron gained or lost. Which fundamental particle is involved? The electron. So this is gain an electron. Oh, sorry, positive. My bad. Lose an electron, gain an electron. Obviously, we're talking about the electron. What particle is not involved? The proton. The proton number never changes. That's not going to be something that's going to change with inside of chemistry. All I can do is change the number of electrons. Okay, so I want you to notice something on your periodic tables. So these periodic tables right here. If you look on the legend in the bottom right-hand corner, it says, not the bottom right-hand corner, that's density. The one right above that says oxidation state. These are typical oxidation states for atoms. And so if you go to sodium, you can see there's just a 1 right there. And so that means that sodium will form a +1 charge when it goes into a compound. And it does that again. How does it become positive? Because it lost electron. In this case, it lost 1 electron. If we move over to magnesium, there's a 2 written there. And so how does something become +2 charge? It loses 2 electrons. Okay, so let's almost everything that happens for us, it's not a molecule or an atom. What it is that you're taking is an ion. So like when somebody is anemic, they're said to have low blood iron. They need iron in their body. It's not iron itself. It's actually iron ion. It's a charged particle. Again, sodium, that sodium, you actually need that sodium in your body, and potassium and calcium, all of those things help regulate your heartbeat. And so if you look at each one of those, the sodium has a +1 charge, the potassium has a +1 charge, and that makes sense because they're in the same column. And calcium has a +2 charge, and that makes sense because it's in the column next to the sodium potassium column and underneath the magnesium column, which we just said had a +2 charge. Okay, sometimes the charge isn't just a single atom, it's over multiple atoms. And so I've had you looking at these polyatomic ions over the course of this class so far. I'm expecting you just Google and look at them, because this is, again, this is like the vocabulary of chemistry. So I know this looks a little daunting. There's a lot here. I was in the same position that you were, taking community college chemistry. All I did is I printed that thing off and I put it in my pocket, carried it around in my wallet. When I was standing in line at the grocery store, I looked it up. I pulled it out and just sat there and memorized them. So what is a polyatomic ion? So the word, the prefix poly means many, atomic means atom, and ion means charged particle. So this is a polyatomic ion because it's got more than one atom. In this case, there's 4 atoms, 1 nitrogen and 3 oxygen. And overall, it has a negative charge. So basically, the nitrogen and 3 oxygens have come together and accepted an electron from someplace else. And now they kind of act like a single object. So they're not going to go into a chemical reaction and break apart. They're probably going to go into a chemical reaction and stay stuck together before and after the reaction. So that's why we treat them as an entity, because a lot of the things that you have around you deal with this. So like chalk is CaCO3. This is a calcium and this is a carbonate. Well, here's the carbonate right here. Or baking soda, NaHCO3. There's a polyatomic ion, and here's the polyatomic ion, hydrogen carbonate. So lots of things around us have these polyatomic ions in them. Okay, so again, I know this looks a little daunting, but I'm going to break this list apart for us and make it a little bit easier. So we start off with nitrate and nitrite. Whoa, that's really thick. Don't want that. Make a thinner one. Let that one work. Nitrite. There we go. Okay, so the difference between nitrate and nitrite is 1 oxygen. So over here, I've got NO3 and NO2. And I don't want us to memorize 8 as 3 and 8 as 2, because that's not the situation. The difference is 8 means more and 8 means less. Because if I move down, I have this one here, which is an 8 right next to an 8. And the difference here is 4 and 3. So it's not about a specific number. It's about the fact that the 8 has 1 more oxygen than the 8s. So that makes it a little bit easier. If you can remember that nitrate is NO3, then nitrite is NO3 minus 1 of the oxygen, so NO2 with a minus charge. Okay, what if there are more of them than just 2 options? So over here we've got nitrates and nitrites and phosphates and phosphites and sulfates and sulfites. What if there's more? Well, let's come over here. I've got an 8 and an 8 and an 8 and an 8. So there's a little bit more to it, because over here I also have a per and a hypo. So chlorine will make 4 different polyatomic ions with oxygen. 1 oxygen, 2 oxygens, 3 oxygens, or 4 oxygens. So what chemists have done is they've divided these guys up in half, cut them in half, and said these are the ones with more oxygen, and these are the ones with less oxygen. Okay, and now how do I divide up the halves? So now what I'm going to say is per, which means more. So this is basically saying more. Well, this one's only saying more. And this one is saying less. And hypo is less. So that's it. Less, more, and more. Sounds kind of funny, but that's how it works. So I get it. That's a lot to put together. But once you've got that taken care of, look what happens down here with the bromates. And then look what happens down here with the iodates. The pattern is identical. Ates, ites, pers, and hypos. So if you get one of them taken care of, then you've got, that's 12 of those guys, 12 total if you've got the first 4 taken care of. Okay, I'll go ahead and erase all this. Another option that you're going to see is, this is hydrogen sulfate. So hydrogen sulfate is going to differ from sulfates because there's a hydrogen here. So what happens to it besides just an H being added? What happens is this was a charge with a +2, and now this is only a +1. So the hydrogen comes as an H+, and so it cancels out one of the negatives that was in the sulfate, and now it's just HSO4 with a minus charge. Same thing happens with the hydrogen sulfite. Looks just like the sulfite, except it's got an H on it and the charge is dropped 1. So phosphates are going to do the same thing. So here's a phosphate with a -3 charge on it. And now I've got a hydrogen phosphate, and now it's only got a -2 charge on it. Or I can have a dihydrogen phosphate, and now I've got 2 hydrogens on it and only a -1 charge. So the charge keeps going up, becoming less negative as you add hydrogens. If I add a 3rd hydrogen, then the charge goes to 0. And instead of it being a polyatomic ion, it will be H3PO4, which is phosphoric acid. The same situation with the hydrogen sulfate. If I add another hydrogen to the sulfate, now the charge is 0 overall, and that's sulfuric acid. A couple of other things to note on this list. I've got acetate written twice. And let me scroll down and show you why that's the case. So these are the 2 ways to write acetate. So C2H3O2 is sort of like saying 2 black Legos, 3 yellow Legos, and 2 orange Legos. Put them together, and they don't tell you how. On the other hand, CH3COO, and sorry, that one looks a little, it's a puny looking little oxygen there. So what I have here, all right, CH3COO negative. So that's what this is. And this is how most chemists write this. So here's a CH3 right here, and that's CH3. And then here's the C, and then OO. So writing it in this format here allows the person to understand what it is that they're looking at, because there's more than one way I can put together 2 carbons, 3 hydrogens, and 2 oxygens. And this is telling me exactly how to put them together. So this format is called the condensed structural formula, because this guy here is the structural formula showing exactly how everything's laid out. And this is the condensed structural formula. So it's, I can't type this one here. It's kind of hard to put into, say, Microsoft Word. But this one up here, I can type pretty easy. All I need to be able to do is put superscripts and subscripts in, and I can get it in. Okay, so that's why acetate is written twice. And then other things to notice on here is there are only 2 that are positively charged. The ammonium ion, NH4 with a plus charge, and then this mercury 1, which is really weird. So this is two hydrogens connected to each other, but each, sorry, not hydrogens, mercuries, but each of these mercuries has a plus charge. But since they're connected to each other, the overall charge is +2, which is why it says +2. And this one, we'll talk about this a lot more later, but 1 means the charge on each mercury. So the mercury has a charge of +1. And so you're a +1, you're a +1, but you can't hang out by yourself. This doesn't exist, mercury with a +1 by itself. For some reason, we're not quite understanding the mercury when it's a +1, when it loses one electron, is always attached to another mercury with a +1 charge. So it behaves like a diatomic, like the hydrogen, nitrogen, oxygen, fluorine, chlorine, bromine, iodine. That's how it behaves, except again, it's an ion. Okay. So there's a little more on these. The acetate turns into acetic acid, and that's the acid that's in vinegar. And so it becomes an acid when that H gets attached. And so it's a lot easier to understand what's going on with the acetate polyatomic ion if I write it like this instead of the molecular way. So this molecular formula isn't super useful. It's just telling you the atoms and the charges, but not how they connect. All right, so we need to talk about something very important, which is oxidation numbers. So this is 100% crucial when I'm naming certain types of ionic substances. So the oxidation number is also the charge of the ion. So I want to know what the charge of this thing is, and I need to be able to figure out what the charge is, or I need to be able to figure out how to put things together once I know the charge. So there are some general rules and some specific rules. The general rules is any element in its atomic form, its oxidation number is 0. So if you just see a carbon written, that means it's not going to be shown as a 0, but it is a 0. Otherwise, they would have given you a charge. So this is carbon atom, meaning this guy has 6 protons and 6 electrons. So it's not an ion. For any monatomic ions, the charge equals the oxidation state. So if I see something like Na with a plus, I'm being told that this sodium's charge is a +1. Or a calcium with a +2, I'm being told that the calcium's charge is a +2. The sodium in this case has lost 1 electron. The calcium in that case has lost 2 electrons. For the polyatomic ion, the sum of the constituent atoms' oxidation numbers is equal to the charge on the ion. So that's a complicated way of saying, when I'm looking at nitrate, the nitrogen and the 3 oxygens have a certain number of electrons, and they got 1 extra one. So nitrogens have 7 protons, so that means they have 7 electrons. Oxygens have 8 protons, so that means they have 8 electrons. I'm going to multiply this by 3 because of this 3 here. And then I have to add 1 more electron because this has an overall charge of -1. So that would be 24, it'd be 32. So this particular, the nitrate has 32 electrons and it has 31 protons. How do I know that? This charge here that's showing me a 1 means it has 1 more negative charge than positive charges. So that's an easy way to do it. Okay, neutral compounds, some of their oxidation numbers is 0. So if I've got something like table salt, NaCl, this thing doesn't have a charge on it. Overall is 0, although we're going to find out that the sodium has a plus charge and the chlorine has a -1 charge. So that's why it's a 0, because they just cancel out. So I want you to grab your periodic table. I want you to look at the first column, and I want you to see lithium all the way down to francium. The charge there for the oxidation number, it shows 1. There are no exceptions to that. Sodium can, when it's in a compound and it's an ion, it can never have a charge other than +1, as well as all the rest of those substances. So there are 0 exceptions to that. The same thing goes for column 2, beryllium down to radium. They're always going to be +2. So column 1 will always lose 1 electron. Column 2 will always lose 2 electrons. Those are the only options it has. Fluorine will always be a -1 charge. So element number 9, no matter what, if it's in a compound, it has a -1 charge. Hydrogen has 2 rules. There's no exceptions to these 2 rules. If it's with a metal or boron, it's a -1 charge. That's pretty unusual for hydrogen, although there are lots of rechargeable batteries out there called nickel metal hydride, and I'm pretty sure the Prius has been running nickel metal hydride batteries for quite some time now. Well, not just the Prius, but all the Toyota hybrids. Does Toyota have an EV? They must have an EV now. But hydrogen is normally with nonmetals, and in that case, the charge on the hydrogen will always be a +1. So you have to go back to your periodic table and look at that little stair step thing. And if the hydrogen is with something on the right side of the stair step, its charge is +1. If it's on the left side of the stair step, it's a -1, except boron, which is element number 5. It'll always be a -1. So if it's with boron or any of the metals, it's accepting an electron away from those substances. If it's with any of the nonmetals, hydrogen gives its 1 electron to that nonmetal. Oxygen's charge 99.99% of the time is going to be a -2 charge. But if it's a peroxide, it's going to be -1. Or if the oxygen has reacted with fluorine, it's going to be whatever fluorine wants it to do. And so I'll show you instances how you're going to know. But if you see oxygen, when I see oxygen, the first thing I think of is, oh, it's a -2 charge. And then I could be looking a little deeper and realize, oh, no, in this case, it's one of those weird instances where it's a -1 charge. The halogens are always going to be -1. That's going to be that column 17 or 7A that starts with fluorine, goes down to acetine, although we don't really care about that one. It's going to have those guys are going to have a -1 charge unless they're with oxygen or a halogen higher. So if I have a compound of chlorine and bromine, so if bromine has made a compound with chlorine, chlorine's charge will be a -1, and bromine's charge would have to be, sorry, not a, I don't know why I wrote a +2, will have to be a +1, because bromine is lower on the table and chlorine is taking bromine's electron away. And we talked about electronegativity, which is the ability of an atom to take electrons. And so in this case, chlorine's electronegativity is stronger than bromine's electronegativity, which is why chlorine takes the electron from bromine. Or you could say that bromine gives the electron to the chlorine. So typically, normal chemical reactions, you're going to see column 1 being a 1, column 2 being a 2. If I skip over the transition metals, then I've got a 3, 4, plus or minus, and then -3, -2, -1. That's usually what we're going to see. So if I'm just looking at substances put together, I'm just going to immediately think of this 1, 2, 3, 4, 3, 2, 1 as what's probably going on. But I might be wrong, and I might have to change my ideas, but I'm going to have to look at the compound and be given specifics to know. So let's do some oxidation number checks here. So this little thing is off of a worksheet called oxidation numbers that's on Moodle. And so I've given a couple of compounds here, and their oxidation numbers. So I'm telling you right now that the oxygen's charge is a +1. How do I know that? Well, the hydrogen's charge is a +1. The hydrogen is with a nonmetal. Oxygen's a nonmetal. There are no exceptions to the rule that hydrogen needs to be a +1 charge. So now, if I have 2 hydrogens, and each one of the hydrogens has a +1 charge, but water has a 0 overall charge, then by default, the oxygen needs to be a -2, because +1 + 1 -2 gives me 0. That's how I can figure out what the oxygen's charge is, being a -2. The next one, that's how fluorine is found in nature, F2. So that is an atom in its elemental state, and so then its oxidation number has to be 0. Okay. That exact same logic is how we get number 3. Neon is just an Ne, and in nature, the neon's charge would be 0. The chlorine in this case has a -1 charge, because I'm being told straight away that the chlorine's charge is -1. All right, let's do table salt. So if I look at my rules, sodium is from rule number 6. It's a group 1 metal. So by default, its charge has to be +1 charge. So what's the chlorine's charge? It has to be a -1 charge. I don't even have to look anything up about this halogen, because if sodium's a +1 and the overall compound has a charge of 0, and there's only 1 of each ion, then the sodium and chlorine combination has to be +1 -1, because that equals 0. That's we're trying to get to in the case of number 5 to 0. Number 6, we're also trying to get to 0. So I've got hydrogen here, and hydrogen is with a non-metal. So if hydrogen is with a non-metal, in this case bromine, then the charge has to be +1. That's the rule. Then again, bromine's charge has to be a -1, because there's only 1 of each, and I have to cancel to get to 0. All right, number 6. rule number 7 we had up there, specific rule, is that column number 2 in a compound has to be +2. You can look on the periodic table and see there's 2 down there for the oxidation number. There are no other options. So if the magnesium is a +2, and I've got one other oxygen atom in the compound, the oxygen is forced to be a -2, which is fine because that's what oxygen wants to be. Okay, this one's a little harder. So we're going to do, not harder, but more complicated. When I was in your position, this is what I did to figure out what the oxidation numbers of each atom would be. Okay, so when I'm done with all of these, I have to equal 0 has to be the overall charge. Okay, so I've got hydrogen with non-metals. All right, that's fine. Hydrogen's charge with non-metals is a +1. So I got +1s and +1s. I don't have a sulfur rule, but I have an oxygen rule that says oxygens are -2. So you're a -2, -2, -2, -2. So this gets me -8. This gets me +2. And so this has to be a +6 to get me to 0. So the sulfur's charge is a +6. So here I would write sulfur +6 and oxygen -2. I only write it once, even if there's more than one atom there, because every atom, every one of those ions has to be exactly the same. So I don't need to write H+, because all of the H's have a +1 charge. I don't need to write O2 4 times because all of the O2s, all of the oxygens have a -2 charge. Okay, the next one is a little different. So how is this next one a little different? Why is this not erasing for me? Huh. That's super weird. There's evidently a pen is not happy. I'm gonna pause this. I'll see if I can fix it. Be right back. Okay, got it. So this one's a little bit different because in this case, we're actually looking for something that has an overall charge. So I've got a chlorine and I've got 2 oxygens, and instead this needs to equal a -1 charge. So if I look at my rules, the oxygen has a -2 charge, so they both have -2 charge. I want to write down a -1 charge for the chlorine because it's a halogen, but I can't because something in this has to be positively charged. And so the oxygens have a higher electronegativity, so they're going to be the negative thing. And now the chlorine has to do whatever the oxygen wants. So how do I go -4 to a -1? This chlorine's charge is a +3. That's it. So I got a Cl with a +3 charge and 2 oxygens, each with a -1 charge. Okay, so what happens if instead of me doing chlorite, I do chlorate? Okay, so for chlorate, I have a chlorine, but this time I've got 3 oxygens. And the oxygens charge are a -2. I'm still looking for a -1 overall. So this time I have to have a +5. +5, -2, -2, -2 leaves me with a -1. So chlorine's charge is a +5, and oxygen is again a -2 charge. All right, let's do another one. So now we've got chromium, 2 of them. And I've got 2, 3, 4, 5, 6, 7. That's only 6, 7 oxygens. So we've got a -2, -2, -2, -2, -2, -2, -2. So that's -14. And this needs to end at a -2 charge because that's what I've got with dichromate. And so how do I get to a -2? If you're a +6 and you're a +6, that gets me to +12. And so that cancels out 12 of my 14 negatives. So now I'm at a -2. Okay. So my chromiums are a +6 and my oxygens are still a -2. Okay. This next one, we're back to a molecule. So my overall charge for this one has to be a 0. So I will have an N and an H and an H and an H and an H and an F. And again, overall charge of 0. Okay. So my hydrogens are with non-metals, so they're each +1. My fluorine doesn't have any other options. It's a -1 charge. And so how do I get to 0? Looks like a -3. So -3 -1 gives me -4. And here's +4. That gets me to 0. Okay, so I've got a nitrogen with a plus, sorry, not a plus, a -3, hydrogen with a plus, and fluorine with a -1. Okay. So the next one, I've got a nitrogen and 3 hydrogens. The overall charge is 0, plus, plus, +1. So again, -3. So NH, or nitrogen with a -3, hydrogen with a +1 charge. Okay, so the next one looks like carbon monoxide. And so I've got a C and an O. You're a -2, so that means you're a +2. Okay, that's it. So +2, O -2. Alrighty. What about the next one? The next one is, sorry, the next one is a C, but this time it's 2O. So -2 -2 +4 gets me to 0. So C with a +4 charge, O with a -2 charge. And if you look on the periodic table, you can see that carbon can have a +2 charge or a +4 charge. And oxygen, again, is just showing that 2, even though it can also be a 1. All right, so the next one we haven't dealt with the transition metals very much. So let's do that now. So I've got 2 different options here. Iron, chlorine, in the 2 different compounds that iron and chlorine make, 2 of the compounds. So let's do Fe and then chlorine, 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 and then we'll also do Fe, chlorine, chlorine. So that's that compound, and that one's that compound. Okay, so I've got a -1, -1, -1, because these are halogens. Chlorine doesn't matter, still -1. And so I need to get to 0. So up here, what gets me to 0? +3. What's here is +2, gets me to 0. So these are 2 different compounds. They have different colors. They have different solubilities. They have different melting points. They have different, completely different chemical reactivity. So that's why I need to identify them differently. And so we'll talk about how to name these 2 compounds a little bit later. So down here, I'm going to write Fe with a +3 charge and chlorine with a - charge, and Fe with a +2 charge and chlorine with a -1 charge. Here is one of those odd substances dealing with hydrogen. So I've got a magnesium and I've got 2 hydrogens. So the magnesium, there are no exceptions to this. The magnesium has to have a +2 charge because it's magnesium. So that's weird. Now all of a sudden I have to write a -1 charge. Is that okay? The answer is yes, because we also had a rule that said if hydrogen is with a metal, it's got a -1 charge, which it was forced to have. So my magnesium has a +2 charge. My hydrogen has a -1 charge. Okay, let's finish up with the weird oxygen ones. All right, so I've got this compound. What just happened? What's going on? HO. Okay, so hydrogens with nonmetals have to have a +1 charge. So what I want to write down is I want to write down -2 for the oxygen, but I can't, because if I did that, my charges don't balance, and they have to balance. So what I am going to do is write down -1. And this, when oxygen has a -1 charge, is a peroxide. So this is hydrogen peroxide, a very reactive substance that we only really see. You guys can only get it in a 3% solution. More concentrated than that, it starts to do really bad things to people and other objects because it's so chemically reactive. Because oxygen doesn't want to have a -1 charge. It wants to have a -2 charge. Okay, so then my answer here is H with a +1 and O with a -1. And that same situation I'm showing you with this next one. So I've got Na, NaOO. Sodiums have to have a +1 charge. They do. So the only way to make this balance is each of the oxygens has a -1 charge. So sodium with a +1, O with a -1. So this is sodium peroxide. Yep, totally exists. Okay, that's what we got here. That's ions, polyatomic ions, and oxidation numbers. Okay. Finish this up.